Well, a warm welcome to everyone joining. Thank you for being here. Get yourself ready, grab a notebook, a pencil, or a pen. Whatever you choose to write with is fine. This is math from the void. Math coming at you pretty much out of nowhere. And today we're going to continue our discussion about radical expressions. We're going to work on simplifying them this time. I made a previous video on multiplying radical expressions, but we really only covered what to do with perfect squares inside of a square root. So today we're going to get a little bit more in depth on how radicals work, how different roots work, and how we can break down and simplify radical expressions, even if there's not, a perfect square or something like that inside of the radical. So first, let's get things started with reminding you of what we looked at last time, something like the square root of 36. Remember that this radical, if there's not a power on there, we pretend there's kind of like a 2 on it. And so square root is basically asking what number times itself will give us 36, and that's a nice whole number. As opposed to something like, square root of 37, what number would multiply itself to give us 37? Well, that's definitely not going to be a whole number. In fact, if you plug this into a calculator, you'll get something barely under 6.1. If I had to guess, like 6.08, something like that. So the point is that we only have whole numbers whenever the number inside of a square root is a perfect square, meaning there's a whole number that multiplies to itself. Something like 49 in a root, for example, would be 7, because 7 times itself is 49. Any number in between 36 and 49 will not come out to be a whole number. So this seems really basic, but we're going to look at some higher powers of roots soon. We're going to look at things like cube roots and fourth roots and even potentially other types of roots. Maybe not in this video. That might be too much. But we're going to start off with the basics. The basics are factoring. Factoring will never go out of style. I want to make that very clear. So what is factoring? Well, you're going to be using factoring in algebra a lot. You're going to be using it in algebra 2. You're even going to be using it a little bit in like geometry classes and trigonometry classes. And you're definitely going to use factoring in calculus. So it's just not going to go out of style pretty much ever, unless you start to study a really particular type of mathematics or something like that. Any math classes should have a healthy dose of factoring in there. So let's just remind ourselves, what is factoring? I kind of already have a little spiel ready here. Let's condense this a little bit though. It's a little long. So factors, what are factors? Factors are units that multiply together to make something called a product. So like two numbers that multiply together, those are factors, and the result is called a product. So when we factor things, we're almost reversing the process of multiplication. It's kind of like we're dividing the numbers out. If this sounds very basic, it should. If it sounds very basic, just you wait. Things will get a little bit more complicated pretty soon. So let's just work out with factoring these numbers. And the goal when we're factoring for the purposes of radicals or square roots is to really get some nice numbers out of this. So whenever you're unsure of what factors you have, you should always consider 2 and 3. Those are like the basic small prime factor numbers that we could use. And I'm going to break this 36 down more, but I do want to point out that this is a perfect square number. So it's no surprise that it's going to be the same number times itself. 6 times 6. I could have also said 12 times 3. I could have also said 18 times 2, or even 9 times 4. Those are all valid, but let's just keep it simple for now, 6 and 6. So this means that 72 is a product, which means like the result of multiplication of all of these numbers together. 6 times 6 times 2, and here is our pair of 6s. That's going to be important to point out. Meanwhile, let's take a look at 280. Whenever you have a 0 at the end of a number, it's divisible by 10. So that's a great number to pull out. And the 10, of course, factors down to 5 times 2. 10 times what? 10 times 28, which y'all should know your multiplication tables enough to know that that's 4 times 7. You shouldn't have to do 14 times 2. If you really have to, that's not the worst, but you got to get with it with the factoring. So this is 7 times 2. And this means that 280 is the product or the results of multiplication when we take all of these bottom factors, you might remember factor trees from when you were younger, 2 times 2 times 2 times 5 times 7, and you'll notice we have this sort of triplet of 2's. So that's basic factoring of a number into smaller parts. Now, why would this have anything to do with radicals or roots? Well, in order to answer that question, let's take a look at some rules of the roots. Now, the way that I want you to imagine these radicals or these roots is almost like a little arena. It's like a gladiator arena. And in that gladiator or warrior arena, we have a battle, right? We have a battle going down. And the radical is going to be indexed, meaning there's going to be like a number on it. There could be a square root. There could be a cube root. There could be a fourth root. All of these things mean something slightly different. So when we're taking these roots, here's the deal. When we have a square root, 2 identical soldiers inside of the root, inside of the battleground, are going to duke it out, and one of them is going to come out. So something like square root of 9 times 9, those warriors are going to battle it out. They are identical, and only one of them is going to survive and come out. So the square root of 9 times 9 is simply 9. Does it make sense now? So they're duking it out. We don't really care which one comes out. They're identical to us. And let's extend that idea to a cube root now. So a cube root is 3 soldiers in, and you're going to see a 3 on this index. So if we had something like the cube root of 4 times 4 times 4, 3 soldiers go in, only 1 soldier comes out. Every time, only 1 soldier comes out. With a fourth root, we would have 4 identical soldiers, like maybe, I don't know, 7 times 7 times 7 times 7. Bonus challenge if you know what that is equal to, right? I know that that's 2,401. It's kind of easy for someone like me, but out of all of these 4 soldiers who battle it out inside of the fourth root, only one of them is going to come out. And it goes on. You get the idea. If I had a fifth root, I would need 5 soldiers to battle it out. So I would need like 2 times 2 times 2 times 2 times 2. But the question here that I want to pose is, what happens if we don't have 5, or if we have more than 5? This tells us how many soldiers go in and battle it out. Well, we'll just take the first 5 in line. Those are kind of the unlucky ones that battle it out. So a 2 comes out as a result of this battle between 5 2s, but then we still have a fifth root of 2 in there. So we kind of just combine them together. So this would be read as 2 fifth root of 2, but it really means 2 times the fifth root of 2. So if there aren't enough for the battle simply doesn't happen. Everyone just stays in the arena. Okay? Oops. So let's get an idea of how that works for ourselves on the battleground. We're going to revisit these 2 numbers that we took a look at. And I'm going to factor 72 in a few different ways to show you that there are many examples. We could call this, right, 36 and 2, and then we could call this 6 and 6. And we could honestly stop here at this perfect square number. We could say that square root of 72 is the same factorization as what we saw up here. Oops. The only difference is that now all of this is going to be in a square root, you see. So the square root of 72 factors in a very similar way to 72. This would be square root of 36 times square root of 2. You guys saw that in the multiplication of radical expressions, so we're just going backwards. And this will just directly turn into a 6, and this stays a square root of 2 because there are not 2 warriors to battle it out. There's only 1 2. So it doesn't have anyone to battle with. It stays inside of the radical. Similarly, here this is the cube root of 280, which is equivalent to the cube root of, what was it, 2 times 2 times 2 times 5 times 7. And if you notice, only the 2s are going to battle it out. There's a batch of 3 2s. So one of them comes out, and then what's left inside are the things that did not get a chance to have a battle. So you can simplify that by actually multiplying those together. It's kind of like multiplying the scraps together. and we would say 2 cube root of 25, which does mean 2 times the cube root of 25. It's just that we're able to write them together. Similarly to if we had like 2x, we don't have to say 2 times x. I mean, you could, but you don't need to say that, right? You could just slap them together and say 2x. All right, so this is just the level 1. We already factored those down. We had a perfect triplet here to fight it out because the arena requires 3 warriors per battle, whereas the square root just requires 2 warriors per battle. And again, we don't write the 2 there. If there's nothing there, we just presume that it's a 2. All right, time to go to level 2. Stepping it up quite a bit. So we have the 4th root of 384. Go ahead and give yourself a shot at that if you'd like. Give yourself an attempt. You can pause the video and try that out. Here's another one as well. Square root of 56x cubed. Give that a try. So we're going to break this down. If you don't know what it breaks down to, that's okay. You don't have to pull these perfect numbers out right away. As long as you see that it's even, you know for sure, okay, I can divide that by 2 in some way. So this is going to turn into 192. And that's still divisible by 2. This is going to turn into a 96. And that is also divisible by 2. But maybe some other numbers will come out as a little bit more obvious. But maybe not. Who knows? Let's do another 2. And this is going to be 48. And then we can take out another 2. And this is going to be 24. And then we can take out another 2. And this is going to be 12. And then we can take out another 2. And this is going to be 6. And then we can take out another 2. And this is going to be 3. Wowza. So we have a lot of warriors ready for battle all the way up to that. Jeez. So let's take a look at this. That means this is equivalent to the 4th root of, let's just sort of go this way, go that way to count our roots. Or you can go, you can go up if you want. I'm not going to tell you how to count them all, but just make sure you don't miss any and make sure you don't add any extras that don't belong there. So we're going to have 2, I'm going from top down, 2, 2, 2, 2, 2, 2. So many 2s. Got 1, 2, 3, 4, 5, 6, 7 2s. So 1, 2, 3, 4, 5, 6, 7 2s and a 3. How's that going to simplify? Well, we have enough for one battle, but we don't quite have enough for the second battle. So 2 is going to come out, and then we're left with the 4th root of whatever scraps are in there. We just multiply them all together. So we're not going to worry about these. We're going to have 2 times 2 times 2 times 3. That's 8 times 3, or 24. And this is simplified. It's as simplified as we can do it. Yeah. All right. Now, something that's also level 2 worthy, because there's a variable in here. Let's factor this up a little bit. This is going to become the square root of, what does 56 factor into? You should know your times tables with this. This is going to be 7 times 8. Most people do know that. 4 times 2, and of course this is 2 times 2. So let's count all of our warriors. We have 2 times 2 times 2 times a 7. But then what about the x's? We have x cubed. Well, that's pretty easy to break up because x cubed literally just means x times itself 3 times. So now we want battles between common terms. We only want 2 warriors per battle because this is an index of 2, even though it's not written. So a 2 pops out, an x pops out. Those are the victors of these battles. Someone won. I don't know who. Someone did. And inside we have 2 times 7 times x. So we would leave it as 2x, square root of 14x. Great. You're doing great so far. All right, keep it up. Let's do level 3, and then we'll have some closing thoughts. So go ahead if you'd like to pause and give yourself a chance to do this one, and also pause and give yourself a chance to do this one. These are the harder versions. And then when you're ready, come back and you'll see how it's done here. So we're going to break this up into the cube root of, how does 48 break up? We kind of already saw how 48 breaks up above, but that's okay. We'll do 2 and 24, and then we'll do 2 and 12, and then we'll do 2 and 6, and then we'll do 2 and 3. So this is going to be 4 copies of 2. That's 2 times 2 times 2 times 2 times a 3. And then we have 7 copies of x. So I'm going to call it by 3 at a time because that's how many we need for each battle. So I have x3, x3, and then just a single x. That makes 7 of them total. And then we're going to have these y battles, y3, y3, and what do you know, y3. That works out perfectly. So let's have some battles now, shall we? Between these three 2's, they're the same, they're identical warriors. We have 3 x's there, that's a battle. We have 3 x's there, that's a battle. We have 3 y's, 3 y's, 3 y's. And when I say we have 3 of them, I really mean we have 3 copies, not like 3y, y cubed. And not like 3 x's, but x cubed. You get the idea. So a 2 pops out, an x pops out, another x pops out, we'll just call it squared, and then 3 victors of y come out. So 3 copies of y come out. And whatever's left is just things that are not circled. So 2 times 3 is left over. Those are some scraps. And then we have an x left over as some scraps. So I'll put this in parentheses just to be careful so that you understand that the 3 is just on the radical here. This 3 is not like an extra exponent or something. Okay, great. Let's do this last one. Fourth root of 288. Of course, we're going to have to break that bad boy down, right? 288, what does that break down to? Well, it breaks down to 2 times 144. You might know 144 is 12 times 12. You should know that. And this is just going to be 2 times 6, which is 2 times 3. So here's another 2 times 6, and the 6 is just 2 times 3. So let's pick up all the pieces here and put it in a root. This is the fourth root of, how many do we have here? We have 2, 2, 2, 2, 2, 3, 3. So we're going to have 1, 2, 3, 4, 5 2's, 2 times 2 times 2 times 2 times 2. We're going to have 2 3's, and then we're going to have some copies of x and y. Now, in the interest of space, I'm not going to really worry about those in this writing, or maybe I should. Let's be thorough here. Let's not skimp, you guys. x9, well, that is going to require a little bit of extended square root indeed. So x9, I'm going to group these in pairs of copies of 4. So we have x4, x4, and then we have a leftover x, because x9 means that 4, 4, 1 gives us 9. Now these y's, this is what's going to be crazy. We're going to have 4 copies of y and 4 copies of y. And how many do we have total? Go ahead and check. We have 26 copies of y. So I need to do 4 at a time, 4 copies of y at a time, until I have 6 of those groups, and then I'm left with 2 copies of y. So look at all these battles we have going on. 4 warriors per battle, as indicated by the index. There's a battle, 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 there's a battle. Sounds like a tongue twister at this point. There's a battle, there's a battle, there's a battle. So who comes out as a victor? We have 2, we have x, and we have another x, and we have 6 victors of 6 different y battles. And then we're going to multiply this by whatever is remaining. So the scraps are 2 times 3, that's 6 times 3 is 18. We have an x hanging out, and we have a y squared hanging out. And that is how you simplify it. You don't have to put parentheses there, but I was doing that to visually assist you and not think that this 4 is like floating around anywhere else. It's on the radical. And that is the simplified form of this radical expression. So these are tougher when they have higher powers of x and y and other variables, but the idea is the same. There's a battle going on, and this number tells you how many warriors, identical warriors, have to compete. Only one always comes out. Now, to give you a preview, what other kinds of things can we talk about with radicals? Well, so I just want you guys to remember that when we're working with these radicals, the number on the radical tells you how many warriors have to go into each battle. This is very useful. I also want to remind you of some basics like factoring. Factoring never goes out of style, so you can always improve your factoring. Find reasons to factor numbers whenever you get a chance. If you see a big number like 58, just try to break it down, factor it down. It'll give you some good experience. And lastly, when we're simplifying radical expressions, I want you to know that radicals of a different order / index, that's the proper word, are not like terms, meaning they can't be combined. So like the square root of 8 plus the cube root of 8, those do not come together. Those are not compatible. So this is not square root of 16 or cube root of 16 or 2 times the square root of 8 or 2 times the cube root of a, like these are not compatible. And also in general, the square root of a plus the square root of b, this is not the square root of a plus b, okay? So I'm going out of my way a little bit to say what things can't be done with radicals, but my point is just stick to the basics that I'm showing you. Worry about factoring, look for common terms, make sure you're aware of the index on the radical, and that will take you so far in mathematics. Now, to finish up this series in the next video, I'm going to show you how to rationalize radical expressions whenever we have a fraction or like some kind of a denominator. So just to give you a preview, if we have something like 4 over square root of 15, or let's say 5 over the square root of 15, how would we simplify that? And things can be a little more intense as well if we have variable expressions. So if we have 3 over x minus square root of 2, is there some way that we can fix that? We'll look at that next time. Thanks for joining. This is Math from the Void, and I'll see you next time.